Hello, everybody. We are back from summer vacation, and this is the first quiz of the semester. We're in the Fall 21 semester. This is Math 106, formerly known as Math 210. Same course, different number, different name. So we're looking at integral calculus and differential equations this semester. The first quiz problem is just going to be finding antiderivatives. So again, this semester we want to be able to find solutions to differential equations, and one very common step when we're trying to find solutions to differential equations is to anti-differentiate a function. So we need to know how to do that. So in this problem, we basically just threw a whole bunch of different functions together. And this is not like the most complicated set of functions. Almost all of these come by just knowing your basic derivative laws and then making some small adjustments because we also know about the chain rule. So later on, we might have to worry about finding antiderivatives of functions where we have to use, say, integration by parts or integration by partial fractions or more complicated substitutions. But in this one, we don't want to use any substitution. We just want to use our basic knowledge of derivatives. So for this first piece here, and I'm going to give a name, by the way, to this function so I don't have to copy the whole thing. So let me just call this f of x. So I'm trying to find an antiderivative, so I'm going to write down this symbol here, right? Like this tells me I'm finding an antiderivative of f. And for the first piece, okay, I have a constant, and we know that if you find an antiderivative of a constant times a function, the constant just comes out. So I'm going to be able to copy this 25. So really the piece I'm worried about anti-differentiating is the x to the 74th power. All right, well, there's a little power rule. Power rule tells us that when n is not equal to -1, that an antiderivative for x to the n is 1 over n plus 1, x to the n plus 1. So this tells us that all we have to do is increment the exponent on the x by 1. And so we'll end up with x to the 74 plus 1, which is 75. And then we divide by that new exponent. So we can divide here by 75. All right, and of course we know this is going to end up being 1/3. Cool. All right, we go to the next one. So again, there's this 5 and this minus, and we know we can just kind of leave those to the side. And what I have left over here then is 1 over 3x minus 2. And, well, this 3 and the minus 2 are kind of annoying, so let me just pretend I didn't have those, right? If I just had 1 over x, this would be a form we actually know. So the power rule had this extra condition, right? We don't allow n to be -1. Because when n is -1, well, then you have 1 over x, right? X to the -1 is the same as 1 over x. And in that case, an antiderivative is the natural log of the absolute value of x. So I'm just going to guess that the answer here is the natural log of the absolute value of 3x minus 2. Okay, now how would I check if this was correct? Well, I could take a derivative, and I know the derivative of the natural log is going to be 1 over the input, but then I have to use the chain rule. So I would get 1 over 3x minus 2, which I do want, but then the chain rule makes me multiply by the derivative of 3x minus 2, which would give me a 3. So I'd have to multiply by 3, right, if this was actually, if I was taking the derivative here. And I don't want to multiply by 3, but I have to, so I can compensate by dividing by 3. So if I divide by 3 and then I multiply by 3 when I take this derivative, they'll cancel each other out, and I'll just be left with 1 over 3x minus 2. All right, so that handles the second factor, or sum end. Okay, what about the third one? Well, this is actually just another version, all right, of a power rule problem, and maybe we're going to have to work a little harder with, adding 1? Okay, that's just the way it goes. So first I have this plus 4, I can copy that. I'm going to have an x, and now I need to raise it to, well, power rule again says you add 1 to the exponent. All right, so this is where you have to remember how to add 1 to fractions. So 2/7 plus 1 is going to be 9/7. Right? 2/7 plus 1, you can think about it this way. That's the same as 2/7 plus 7/7, which will be 9/7. And then we have to divide by 9/7. Right? So that can go down here. Now, if you want to rewrite this a little bit, remember dividing by 9/7 will be the same thing as multiplying by its reciprocal, 7/9. So this piece down here is 4 times 7/9, okay, or 28/9 if you prefer. Cool, so we get the third sum end. All right, now we head over to this sine function. All right, well, we need to know the derivatives of sine and cosine, and they actually are pretty, consistent, right? So if you take the derivative, and I'm just going to abbreviate sine with s, I take the derivative of cosine, or sine rather, I get cosine. And if I take the derivative of cosine, I get negative sine. And if I take the derivative of negative sine, I get negative cosine. And then it just cycles around back to the top. All right. So this is what happens if I take the derivative, right? And again, it's going to cycle when you get to the bottom. If I want to do antiderivatives, I just go the other way. So if I have a negative sine, which is what we have, all I have to do is go up. That's a cosine. All right. Now there is this 4x minus 1, but I'm just going to pretend for a moment that wasn't there. I say, okay, I'm going to assume that it works just the same way as if it was an x, and I'll put down the cosine of 4x minus 1. Now, it's a good first guess, but we have to check. And I can check by taking the derivative. Now I know if I take the derivative of cosine, I'll get negative sine. Check. But there's that chain rule again. I have to multiply by the derivative of 4x minus 1, which is 4. I don't have a 4 here, so to compensate, I divide by 4. Now that chain rule is just going to cancel out this 1/4. Cool. All right, and we move on now to this exponential. Hey, exponentials, those are nice, right? We know that an antiderivative of e to the x is e to the x. So let's see here. I copy the minus 3. I'm just going to assume again that it works the same way with 2x as it does with x, and I'll just copy that down. Of course, I want to check this. If I take the derivative, though, of e to the 2x, I get e to the 2x, and then by the chain rule, I have to multiply by a 2. So I compensate by dividing by 2. And there we go. All right, moving on. Ooh, my goodness, this one looks scary. Let's see, we have a cosecant of something times a cotangent of, well, it's something, but it's the same something, right? Okay, that's really handy. Where have we seen that before? Cosecant times cotangent. Well, it's kind of like secant tan, right? Now, secant tan, that was the derivative of the secant function. So this is just cosecant and cotan, right? The law of co tells you just have to replace the secant with its co-version, cosecant, and then toss in a negative. So if I have cosecant of x and cotangent of x, this is going to be the derivative of the cosecant provided I toss in a negative on one of these two sides. So I'll put it on the left here. Okay, so, well, actually, maybe I should put it on the right because I really don't want a negative here. I want a positive, so let me put it on the right. All right, so if I want to have an antiderivative for cosecant times cotan, I should use the negative of cosecant. Now again, there is a 4x and not an x, but we just play the same game over and over and over again where we assume it'll work just the same way. So I get minus the cosecant of 4x. And again, if I take the derivative, I know I'm going to have a chain rule application that makes me multiply by 4. So I'll compensate by dividing by 4. All right, we're down to the very last one. This last one, oh my goodness, what an interesting looking function. All right, well, if you happen to know your derivatives for inverse trigonometric functions, then this should look reasonably familiar. So let's move down a little bit. If you have the arc sine of x and you take its derivative, this is 1 over the square root of 1 minus x squared. And so if we jump back up, you see this is of that form, 1 over the square root of 1 minus, well, not x squared, but something squared. And that something, just like in all these other examples, is just a linear function of x. And so we're going to be able to play this exact same game. So we're going to say arc sine, instead of x, of 3x plus 1. Again, if we take the derivative, the chain rule would give us an extra 3 factor, so we'll divide by 3 to compensate. And so, at long last, we have found an antiderivative for this function consisting of these, 4, 5, 6, 7 summands. Crazy. All right. Let me know in the comments if this is helping.